Hey guys, I'm Margia. About a week ago, I made a video about programming for your programming language on the web, for the browsers, and in it I have mentioned some terms from the compiler theory, which I tried to briefly explain there. However, I received some feedback that my explanations are very unclear there. So I will try to make another video in which I explain the basics of the compiler theory as clearly as I possibly can. So, what is my experience with making compilers? Where I have made two compilers for my programming language called AEC. One is targeting x86, that is Intel and AMD CPUs. They share the same assembly and machine code. And the other one is targeting WebAssembly, so it can be run in modern browsers. Here is an example program in my programming language which can run on both WebAssembly and x86, that is on Linux and FreeDOS. So about the Tokenizer. Tokenizer is a part of the compiler, and it's usually the first part of the compiler that tells other parts of the compiler when one word in a programming language ends and where another begins. In English, that is easy to do because words are separated by spaces. In programming languages, programming languages are more like Japanese writing than like Latin alphabet. In that Japanese writing, it has mechanisms for separating the words, but those mechanisms aren't as trivial as they are in the Latin alphabet. Japanese is a very agglutinative and suffix-heavy language. That is, it has very few prefixes, but it has, and almost all grammatical affixes are suffixes. Now, the roots of the words in Japanese writing system are usually written in kanji, that is Chinese characters, and grammatical affixes are written in hiragana. And so basically, whenever there is wherever a string of hiraganas end and kanji, and there is a kanji that is probably another word in Japanese. That is not as trivial as it is in English, but yes, Japanese people can easily tell where one word in their writing system ends and where another word begins, and most Japanese will tell you it is even easier to read than if text was written entirely in some syllabary, hiragana or katakana, and the words would be separated by spaces then. But to us foreigners, that is complicated, and well, a computer is a foreigner to programming languages. Then after the Tokenizer, some programming languages need a lexical analyzer that is a part of the compiler that tells us what type of the word in a programming language is each word. And it is, in most programming languages, it's not necessary, but in C, which has many compilers, it is necessary because of the, well, type-def keyword. It is usually considered a bug in the C programming language, and it basically you can't tell whether generally you can't always tell whether something is a variable name or a type name without knowing the whole program in C. Then after the Tokenizer or Lexical Analyzer comes the Parser. Parser is the part of the compiler that tells other parts of the compiler which word is connected to each word grammatically, that is syntactically. There are many frameworks that are supposed to make writing parsers easier. YACC, yet another compiler is, well, probably the most famous one. No, I didn't use them in my compiler, simply, well, they take time to learn and it's not worth it if you are going to write one or two parsers. Here is an example from the Latin language of what I mean when I say that a word is connected to another word grammatically. For instance, in this sentence from the Julius Caesar's the Bello Gallico, there are words nota and fama next to each other, and if you know only a little bit of Latin, you will probably guess that they are connected grammatically and that this is some kind of a pleonasm, that it means noun rumor, nota meaning noun and fama meaning rumor. But that's wrong. In fact, nota is connected to loca and it means noun places or noun locations, even though nota and loca aren't next to each other and nota and fama are next to each other. So in such situations also happen in programming languages. They are resolvable, but not always trivially resolvable, and the knowledge about how to resolve them should be kept localized, or else, well, the compiler will be very messy if it will work at all. Abstract syntax tree is, well, that's or AST for short. That's a common term in, well, computer science, especially compiler theory. That's a structure in the memory of the computer created by the parser. And here you can see how one of my compilers, the one targeting x86, is capable of drawing an abstract syntax trees if it is run in a browser. So here we can see the abstract syntax tree it has drawn for 1 plus 2 times 3 on the left, and on the right there is an abstract syntax tree of 1 plus 2 times 3, with 1 plus 2 being inside parentheses. And here you can see basically to calculate the result of the operation on the top of the abstract syntax tree, you need to calculate its so-called children, the left child and the right child, or if it has more children, then also those children before you can calculate it. And here is how they are presented. After the parser, there comes in most, well, I suppose in all programming languages, Semantic Analyzer. And it's necessary because, first of all, not all sentences that the parser accepts are syntactically correct. Parser only needs to, it's not a job of the parser's job is basically to assume that the text is in the programming language is syntactically correct, and to produce, if possible, a syntax tree for that, not to check whether that syntax tree is valid. And so there needs to be some part of the compiler that checks whether that syntax tree is actually valid. And the same seems to be true for the parser of natural languages in the human brain. We know that because there are many so-called grammatical illusions in natural languages. That is, sentences which sound acceptable at first when we hear them, but when we try to analyze them to determine precise meanings, we see they are actually ungrammatical. The most famous such is, without a doubt, comparative illusion. For instance, more people have been to Russia than I have. At first, this sounds acceptable, but it is actually grammatically incorrect, and no coherent meaning can be attached to it. And also the parser does not denote parts of the sentence, subject, object, and predicate. Those are called types in programming languages, and that is also the job of Semantic Analyzer. Now, after the Semantic Analyzer, there comes finally the compiler. Now, the word compiler has two meanings. In the broad sense of the word, that is a program that converts code written in one programming language to another programming language, usually machine code. Examples of that would be GCC, CLang, Visual Studio, C++, and so on. You probably know countless compilers in that broad sense of the word, but in the compiler theory, it is, when we say compiler, we usually mean a compiler in the strict sense of the word. That is a subprogram that converts an abstract syntax tree into assembly code. And it's also a compiler in the strict sense of the word, is also sometimes called code generator. And LLVM is a framework supposed to help with that. I didn't use it, and in my opinion, it doesn't help a lot, especially when you are targeting WebAssembly, because the WebAssembly binary toolkit, the assemblers and linkers for WebAssembly are very featureful, and basically they do most of the things, or at least many of the things LLVM is supposed to do. LLVM is also supposed to help you optimize your code, but I didn't bother to do those things. So the compiler, in the strict sense of the word, outputs assembly code. Now, assembly code is, machine code, ones and zeros that the computer understands, full of shortened forms to be, so that it is easier to read and write. And an assembler is a program that replaces those contracted forms with ones and zeros. Of course, modern assemblers do a lot more than that, but that's basically what they do. I think one of the best explanations for the difference between assembly code and machine code is, assembly language reads to a computer, similar to what this sentence, BTW, I am HO, you are taking it too serious. What this sentence reads to an English speaker unfamiliar with the internet slang. Then after the assembler comes the linker. And what's a linker? Well, you see, a file with raw machine code is not very useful to a computer, because first of all, how can the computer even know it is a machine code rather than image or a sound file? Images and sound files are also ones and zeros to a computer. They are also represented by ones and zeros. So how can it differentiate between them? There needs to be a program, and it's called the linker, that adds some headers to those files so that they can actually be recognized as executable files for a certain operating system. And there are essentially two very different types of linkers. That is a dynamic linker. That one is usually, a part of the operating system, and not actually, it's not connected to the compiler. And when it's using a dynamic linker, the executable file only contains a part of the program, one that is specific to that application, the core of the program, the algorithm. And it calls external so-called dynamic linking libraries that are assumed to be present on the operating system, which an obvious downside of using a dynamic linker is that you are assuming those external libraries which your program uses are present on the operating system, which they quite possibly may not be there. And then there are static linkers. They are usually accompanied with compilers. Compilers are usually accompanied with them, and those are And when using static linkers, executable files contain everything necessary for the program to run on some operating system. And the downside of using a static linker is that, well, the executable files, of course, take a lot of disk space. Then, if you are using a static linker. And that was it. I hope I have cleared up some confusion. Thank you for watching.